right, hey y'all, it's Mr. Kyle Myers Mathematics, and let's just jump into it. We are on number 59. A lake initially contains 2,000 fish. Okay, that's a pretty good amount of fish. Suppose that in the absence of predators or other causes of removal, the fish population increases by 6% each month. However, factoring in all causes, 150 fish are lost each month. Explain why the fish population after n months is modeled by blah, 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 with p sub 0 equaling 2,000. So this first part, part A, I don't know if I'm going to write down what I would say the answer is, but you can play it back if you miss something. I wouldn't go word for word with what I say. Put some thought into it, put it in your own words. But essentially, what they did here is they wrote out a recursive formula, p sub n and p sub n minus 1. So they wrote out a recursive formula, which is easier than writing the explicit formula. So it's kind of a cop out that they wrote the recursive because it's easier. But I wouldn't include that in the explanation. The reason why the fish population after n months is modeled by p sub n equals 1.06 p sub n minus 1 minus 150 with p sub 0 equaling 2,000. The reason why that works is because that's exactly what the problem says. The initial population is 2,000, so p sub 0 would represent 0 months have transpired, which would represent the initial amount, which is 2,000. So that's why p sub 0 is 2,000. The population increases by 6% each month. Factoring in all causes, 150 fish are lost each month. So the population is increasing by 6%, 6% of the original amount at the beginning of that month is what they're going off of, not 6% at the end. That would be a little different. So the reason why it's 1.06 p sub n minus 1 and then just minus 150 is because, according to PEMDAS, you would do timesing before you would do minusing, meaning we're going to times by 1.06, which is 1 plus 0.06. So 1 plus 0.06, meaning the initial amount plus the increase of 6% plus the 0.06 of the initial 1.06. That gives us the new amount, 6% more, and then we take off 150 afterwards. And that's kind of how they're explaining it in the problem. They could have been a little better at explaining it, but not a bad explanation. So we're going to do minus 150 at the back end because that's what happens after we add the 6%. So hopefully out of all that, you can put that in your own words and make it a little more succinct than that too as well. But that would be the explanation that I would give, more or less. And then for part B, how many fish will be in the pond after 1 year? This is kind of a trick question because you might think like, oh, I'm just going to plug in 1. But no, the amounts that they're quoting here are per month, not per year. So you would need to find out how many fish are in the pond when n is 12. So recursively, we'd have to do this one step at a time here. So we would say, okay, so when n versus when p sub n. So when n is 0, that's our initial amount. P sub 0 is 2,000. They told us that. Right? But what about when it's 1? Okay. Well, we would say that p sub 1 is equal to 1.06 times p sub 1 minus 1, aka p sub 0 minus 150. Right, so then p sub 1 is equal to 1.06. P sub 0, we know, is 2,000. So this would represent what's happening in the first month. We're going to get 6% increase in a month, but we're going to lose 150 fish. Okay. So let's see what that would actually come out to be. 1.06 times 2000. Let's see, 1, 2, 1, 2. You don't have to do this by hand, but I thought it would just be fun to do it. So this would be 106 times 20. So that's going to be doubled, and then I add a 0. So that's going to be 212 with a 0. So we only gained 120 fish, but we're going to lose 150. So actually, because we're losing 150 fish and the percent gain is less than the fixed amount that we're losing, we're going to end up with no more fish eventually. It looks like here is what's going to happen. So eventually we'll have no more fish left. Minus 150. So minus 120 would be exactly 2000 again, right? But then minus 30 more would be 1970. Right? So that's what happens in the first one. Now, what we can do is, in order to speed this up, I can actually type this in. I'm going to type it into Desmos, but you can type this in whether you're using a scientific or a graphing calculator. What I'm going to do is I've already got a function pulled up here, and I was already writing in. I've got some stuff saved from a previous problem here. But what I'm going to do is I'm going to make a function for my recursive. Now be careful not to actually look at the function and look at the trend and misinterpret that trend. But we're going to write the recursive here. So it's going to be it's 1.06 times p sub n minus 1. So I'm just going to write x. And then it was minus 150, right? So if I graph that as a function, yeah, so 1.0, making sure I got this right. 1.06, 150, yeah. So if I graph this as a function, it actually would just graph like a line. And if I scroll out a little bit, you can see the line. So there's the line. It's just a line if I try to graph it. I don't really care too much about the graph though, right? So I'm going to zoom back in a little bit so we don't get distracted by that. Basically, what I'm going to do is I'm just going to find out specific f values, and then I take those solutions and I plug them back in, right? So f of 2000, we can just confirm our answer. F of 2000, 1970. Awesome. We got the right answer. Now what we do is we take that number and we plug it back in. So I'm actually just going to copy paste it, but if you're on a graphing calculator, you'd have to just, write it down or just remember what the number is. So I get this. Now we're getting into decimals, so we would need to round to the nearest whole number because this is amount of fish. You can't have 0.2 of a fish, not on a live fish, anyways. So 1938.2, we would say that's 1938. We would round to the nearest whole number. For sake of being accurate, I would probably go ahead and leave the decimal in as we go to more and more iterations, just so that I'm getting a more and more accurate number here. But let's go ahead and write some of these numbers down. So I'm going to move this over here. Let's actually move this over here. Yeah, I like this better, actually. So that it's over here. And I'm going to write this right here, put this right here. Yeah, there we go. That way it's kind of like underneath where my head is, and then you guys can still see it, but I can still write stuff on the board. I like that. Okay. So 1970 is the first one, and then 1938.2. So 1970, and then 1938.2. Okay, and then the next one, 3. We could also write out the explicit formula, and that would actually be a little bit faster. I don't know which one your professor's looking for. The recursive, using the recursive is like slower, but it might be what your professor wants. So I don't know. So we get that number, and then 1938.2. So I'm gonna just copy paste. So if you want the explicit formula for this, let me know in the comments below. I can do it. It wouldn't be that difficult. I usually don't write the explicit formulas because on the past few, the explicit formulas have been crazy, or I know they would be crazy. I didn't actually find out what they were. but I know they would be really crazy. This one wouldn't be that bad, but just to try to have a little bit more of a succinct video, I'm gonna probably leave those out. I'm gonna round. So 1904 is what I'll write down on the my T chart here, but I'll keep the decimal when I go to plug it back in. So I'm actually going to take off that 0.2, and then I'm going to do 1904 for this one. So wait, why am I subtracting that? I don't know. Let's call it. Let's get rid of that though. So 1904. Yeah. So in the T chart, I'll just write the amount of fish that it would be. Okay. Copy. And if you're just looking for the answer, you can scrub to the end here, I guess. But I actually have the answer. And you can get the answer for this because you could pull it up because it's an odd number. So if you want, you can either scrub to the end or just go ahead and click on number 59 if you're on there, the Stax Calc 2 textbook, and then just you can find out what it is because it gives you the answers for number 59 because it's an odd. 1869, it would round up. 1869. Come on. Doesn't want to write. There it goes. 1869. Okie dokie. I'm actually, you know what I'm going to do is you guys can see this. You guys can see how I'm doing it. I'm actually going to pull this all the way over. And then that way it's not like I don't have to keep pulling it up every time. I can just leave it pulled up over here on my monitor. Okay, so I'm typing that in and I'm getting 1831 now. And again, the number I'm quoting is me rounding it to the nearest whole number. But the number I'm actually using in each iteration is the decimal number. I'm using the unrounded or mostly unrounded version for this. So for 6, now I'm getting down into the 17s here. So 1791, that will round up as well. And it looks like we're halfway there. So I'll probably use the next row for the next set here. So click this. So in and piece of in. So now 7. So I'm going to copy paste again. Sorry, this is a little tedious. That's just the way the recursive formula works. 1748. Number 8. And like I was saying, if you want to see the explicit formula, if you find the explicit formula, this would go a little bit faster. However, this doing it recursively is simpler, and it might be what some people's professors are looking for anyways. So that's why I wanted to go ahead and do it this way, because they might just want to see the work for this. I can definitely see professors asking for something like this, like make sure you show all the steps, all the recursive steps. And maybe it's so that you do it the hard way the first time, so that the next class the professor's like, oh, by the way, let me show you this easy way. And then you'd be like, oh yes, that's so much easier, thanks professor. And then you're like, oh wow, what a great professor, he showed us an easier way to do it. But really he knew the easier way the whole time and he was making you do it the hard way. So all right, copy. Just projecting here. Maybe your professor's like that. Maybe they're not. Now I'm getting 16.0. That would just barely round up to 16.05. Almost there. We're 2 away. And then we'll see what they did because I wonder if they were rounding as they went. They could have been. Now I'm getting 1551. Ooh, a palindrome. And for number 11, which is a palindrome as well. That's interesting. Little treat there. The palindrome value of n is a palindrome answer. 1494. 1494. I'm actually curious to see what they have. I really am. So I'm going to pull up the answer here and see what they ended up getting. So 60, no, 50, 59. Without losses, population would obey, blah, blah, blah. Their answer explanation for part A is really dumb, actually. Their answer says without losses, the population would obey P sub n equals 1.06 P sub n minus 1. The subtraction of 150 accounts for fish losses. That's it. That's all they say for the answer. Part B, after 12 months, we have P sub 12 is partly equal to, oh, they did do it the same way I did it. Okay, 1494. So they didn't round as they went. They kept using the decimal as they went, even though that decimal amount of fish wouldn't make sense for that n value. Okay, cool. So they ended up doing it the same way I did it. So those are all your different values. Hopefully that's helpful. Go check out the 5 math mistakes everyone makes and how to avoid them. It's a free PDF guide I have on my website, myersmathematics.com, which is down in the description below. And I'll catch you in the next video. Blessings, y'all.